We're delighted about this ALCG grant, which will allow us to better understand the inner workings of supernova explosions. Supernovae are extremely powerful explosions of massive stars. For several weeks, they can be so bright as to outshine an entire galaxy. But we cannot look inside these explosions with our telescopes to figure out how they work. For that, we need supercomputers like Gaudi. We can already simulate supernova explosions quite decently, but to obtain really accurate models, we need to better resolve the delicate structures in the turbulent flow behind the shockwave of the explosion. And we need to put in more and more detailed physics into them. For example, because the interior of the star consists of ionized plasma, we can have very strong magnetic fields in there that affect the explosion. Our high-resolution simulations on Gaudi will allow us to much better understand how these phenomena play together and how supernova explosions are energized.
Well, we'll not only learn how the explosions work, but also about the gravitational waves they emit as they explode. Predicting the gravitational wave emission will help us to make the first ever detection of a supernova with gravitational wave detectors. Our simulations will help us understand how a supernova gravitational wave detection is related to the properties of the explosion and the young neutron star formed at the core.
Almost all chemical elements heavier than hydrogen and helium are forged inside stars. But many of these elements are really only made and released in the supernova explosion of a massive stars. These are elements such as calcium, silicon, oxygen, and other elements necessary to life. But to understand how that process works in detail, we do require high-resolution supernova simulations in 3 dimensions, such as those that we can now do with this ALCG allocation that we received.